about something, that means we are trying to bring in a new paradigm, a new definition of information. That means we are trying to see
Recording in progress.
whether I can make that. What we can do is, like when we are bringing a new protocol over here, this new protocols and new ways of communicating with each other, and this new way that we are saying that we are talking about this quantum information, then we first need to realize that what actually was happening in the classical scenario and why am I moving to this quantum information scenario. That means first we should understand that what at all this quantum theory can give us an advantage so that I can use them in information processing protocols and also in computational tasks. So because the main idea is that whether quantum theory is allowing me the access to some of the resources which can help us to surpass the information processing protocols that we have at present provided by classical information theory. And we would also like to see that what are those resources which can be helpful in using in quantum computation. So these are the main ideas. That is, what advantage I am getting, what are the resources that I am not getting in the classical scenario, so that I can use them in the quantum scenario. So one such resource that actually I will be talking about today is the resource of quantum entanglement. And then we will see that given a particular system, how do I say that that particular system is indeed entangled? And then what I will try to see is that how can I use that quantum entanglement for various information processing protocols. Some of the key features that we will see in this session. So to go by that, one thing we need to realize that when we talk about this classical processing, then we are actually working with what? We are working with 0 and 1. That means what we are doing? We are taking strings of, like you can have a string like this. 1, 0, 0, 1, 1, 1, 0, 0. So this is a string of length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is a string of length 12. And in each of the positions over there in the string, what I have is, I have either a 0 or a 1. So that means, how am I storing information in case of the classical system? In case of the classical system, what I am doing is that I am taking the help of states, which can be either in the state 0 or it can be in the state 1. And that's why in order to manipulate with this, that is zeros and ones, I am taking the help of a mathematical structure. And that mathematical structure is that we are taking the help of Boolean algebra. We are taking the help of Boolean algebra. Now, there is nothing much very like, there is no meaning to get panicked with this idea of an algebra over here. I will not be talking about very technical things over here, but this notion should be clear that what actually is Boolean algebra, which is a branch of mathematics, telling us what kind of advantages or what kind of properties it helps us to use so that I can manipulate with the Boolean strings. So basically what we are trying to do, I have an information and that information has been encoded in a string like this. So basically this is carrying some information, and what I am doing is that at each of the positions I have a 0 or 1. And what is Boolean algebra telling me to do? This Boolean algebra is actually telling me that how do I manipulate with these strings. That means how do I work with 0 and 1. That means those kind of systems which either can be an off state or an on state. That is 0 or 1. That is what Boolean algebra is helping me to do. Okay. So that means if you see that right now at a particular position I have either a 0 or a 1. Either a 0 or 1. Either a 0 or 1. That means if you just try to think the number of possibilities. That is, if I have a string of length 12 and I want to know how many different such strings I can produce. So the number of strings that you can produce is 2 over here, 2 over here, 2 choices over here, So in this way, up to this position, I have 2 to the power 12 choices. That means what I have? That means I can actually generate 2 to the power 12 such kind of strings, and then I can use for information processing. And how do I add two strings or add them, or how can I multiply two strings? How can I? That means basically what I'm trying to do is that how can I concatenate? That means join two strings and give rise to another source of a message that helps me. That Boolean algebra is helping me to do. So this is one mathematical tool that I'm using to understand what can I do with the strings over here. But now imagine a situation in which that this position over here that I have written as a 0. Suppose I say that it is not 0, but what I can do is I can write it this particular position alpha 0 plus beta 1. Now I will come to this notations. What is this 0 kit and what is this 1? So the thing is that basically now what I am saying is that there is a system, there is a state which not only it remains in a state 0 or it remains in a state 1, but it can remain in a possible combination of all of them. And over here this alpha and beta will have a constant, and that constant is that mod of alpha square plus mod of beta square will be equal to 1. I will come more to this. I will explain this why this is happening. But just now concentrate on this particular part. So that means this is allowing you somehow this particular case that you can take half of 0, half of 1. You can take 3 by you can take like 1 by root 2 of 0 and 1 by root 2 of 1. You can take some other combination of 0 and 1 such that mod of alpha square plus mod of beta square remains equal to 1. So it is allowing you to take a possible combinations of zeros and ones. So see, how many possibilities now will you have in this position? You will have now an infinite number of possibilities, because this alpha and beta can take any value just with this constant. So that means now the number of possibilities is not 2 but more than 2. In fact, it is infinite. This is a significant departure that we can see. So then you will be asking me that why do you think, or how is this made possible that instead of 0 and 1 I can have infinite number of possibilities? Who makes it possible that I have a state which looks like this, that is alpha 0 plus beta 1? So then the thing is that this is what quantum theory allows you to do. That means that it not only says that there are states which can be in 0 or 1, but it says that it can be in a superposition of 0 and 1. That means it can be in any of the combinations of 0 and 1. So then the question is, okay, that I understood. So a door of infinite possibility opens in front of me, but I need to tackle it. So this is something that quantum theory is allowing me to do. That means it is allowing me to use states which can be in superposition, which was not allowed classically. So then I understand, okay, this is a very significant resource that I am getting, that is in quantum theory is allowing me to do. So then the question is, okay, I have understood this, that this can give me advantage, but I have to know how do I manipulate with it? How do I work with those kind of things? Because Boolean algebra will not help you to work with this kind of a thing. So then this notion came, or rather we were reminded that now Boolean algebra will not suffice, but rather I should use linear algebra. So what does linear algebra deal with? Linear algebra actually deals with that there will be a kind of a mathematical structure. So in that mathematical structure, every object that we have will behave like a vector. We will call them as vectors. And what we can do, we can add two vectors, we can divide those vectors, we can subtract those vectors, we can multiply a vector by some constant. So these are some of the operations that I can do. So those operations that I can do with them gives rise to certain properties. And what will happen is, what I get over here is known as a vector space. So this vector space will actually help me to understand how do I work with quantum states. Now I'm telling this because that you have already had sessions where some very distinguished person spoke about that what are the basic postulates of quantum theory. What do you mean by a quantum state? What do you mean when you say that a quantum state is getting multiplied by a certain phase factor? So these vectors, that is those quantum states that are appearing, this actually lies in a space. And those spaces are some special kind of vector spaces. Why I am saying special? Because those are known as Hilbert spaces. Because it is a vector space, it is a kind of a special vector space, but over there what happens is that it can be that I can define the angle between two vectors. That means at least I can say when two vectors will be orthogonal to each other. Orthogonal means that they will have a 90-degree angle between them. So this notion of this orthogonality was brought about by some special kind of vector spaces which goes by the name of Hilbert spaces. So that is the thing that we will be working with, because I need those ideas to define, as I said, that now I will look for that another important resource, and that is quantum entanglement. Okay, so then this question arose. Okay, so this is something that comes up, that what is this? What is this entanglement, or what are we trying to exploit? So see, what we are trying to exploit is okay. So what I am trying to exploit is that I am trying to exploit correlations. Correlations. So what is this correlation? So imagine that you have this situation. See, my basic idea is I want to actually use an enhanced communication protocol, or I want to use an enhanced computational task. So what is this correlation that I'm trying to exploit? So this correlation that I'm trying to exploit is, that's why we have to bring two imaginary characters. And those two imaginary characters goes by the name Alice and Bob. Okay, so these are the two imaginary characters that I have brought in. So now we will play a game. What is that game? That game is, suppose there is a referee. Okay, so there is a referee over here. So what will this referee do? This referee will actually give a binary question to Alice, and he will give a binary question to Bob. Now what do you mean by a binary question? It means that referee will give the input as 0 or 1. Okay, so in each of the round of the game, what they will do, the referee will do is, he will give a question 0 or a question 1. 0 or 1. Similarly, he will do the same thing with Bob. 0 or 1. And then, what is Alice and Bob expected to do? Alice and Bob, what they will be expected to do is that they have to come out with an answer. And that answer will be either -1 or +1, or -1 and +1. Okay, so let us understand this game. So the game is that at each round of the game, the referee is giving them either 0 or 1, and Alice and Bob, they have to come up with an answer -1 or +1. So there will be a situation like this, that Alice is given this, Alice's output is +1, Bob's output is -1, given Alice's question was 0 and Bob's question was 1. Okay, so this was Alice's question, the question posed to Alice, and this was the question posed to Bob, and these are the two outputs that they are giving. This is suppose one round. Okay, and what I will do is I will take at each round of the communication, Alice and Bob, at each round of this game, Alice and Bob will not be allowed to communicate with each other. That is the rule of the game, that they will not be allowed to communicate with each other. So if suppose I take this particular case, that I say that the question is X, output is A on Alice's side, question is Y, and output on the Bob side is B. So these are my questions. X and Y denotes the questions to Alice and Bob respectively, and A and B represents the outputs by Alice and Bob. So basically what I am trying to see is, I am trying to calculate probability of AB given X, Y. So this is a probability that I am trying to generate. This is the thing. Okay, so this, what actually I am trying to do is that I have played the game for many rounds, and this is the collection that I am making. That what are the different probabilities. Okay. Now there is a particular quantity, and that particular quantity is S. What is this quantity? This quantity is A0 B0 plus A1 B0 plus A0 B1 minus A1 B1. So the rule of the game is that if Alice and Bob's question are 0, 0, 0, 1, 1, 0, then they have to give the same answer. But if their questions are 1 and 1, they have to give different answers. What I am doing over here is, I am correcting an expected value. That means, as I said, that I have played the game many number of times and I am taking an expected value. Expected value, so this notation is for expected value. This notation is for expected value. So these are the expected values that I am calculating. Okay? And before the game, what happens is, Alice and Bob have been given this freedom that you can define any, you can actually come up with any kind of strategy, because once the game starts, they are not allowed to communicate with each other. So they can make any strategy. Like for example, they can say that whatever may be the question, I will give the same answer. Both Alice and Bob decide this. That can be one of the strategy, or any other kind of strategy that is predetermined. So what happens is that basically that strategy is acting as a kind of correlation between them. Okay, so they are sharing this correlation with them and they are starting the game. So if they start this game, what will happen is, and if you take this quantity, calculate this quantity, then with those predetermined strategies, no matter what is that predetermined strategies, it can be shown that this, the optimal value of this can be only 2. This optimal value S can be only equal to 2. No matter what predetermined strategy they can do, with some calculation it can be shown that it can have this as the highest. So that means, so long as the game was classical, that means they were allowed to use any kind of predetermined strategy. That means an allowed correlation between them. With this classical correlation, they can achieve highest value as 2. Okay. So then the question arose that, okay, now let me do something. Let me allow this Alice and Bob to share quantum correlation between them. That means they are sharing between them a quantum state rho AB. Okay, so quantum state means that it's a state where one of these state is, it is a two-party state. One state is with Alice, the other state is with Bob, and they are sharing this. Then what happens is that it was shown that this rho AB, if it is a bit strongly entangled, that means if it is a bit strongly correlated, then what happens is they can achieve a value of S to be equal to 2 into root 2, which is higher than this one. So that means people were then very struck by this idea. That means so long as you allow to use this classical correlations between them, they will never able to breach the value of 2. But the moment you allow to use an entangled state between them, that means a correlation which is not explained by the quantum correlations, then the classical correlations, then you can achieve a value which is more than 2. So right now it might seem to be you that this is merely a game, but the question is, all information protocols can actually be thought to be as a game like this. That is, where your classical resources, that means the correlations that you have between Alice and Bob, can be used for a communication protocol. So it has been shown over here by this particular game that if you allow Alice and Bob to use a quantum resource, and more specifically an entangled state between them, then they can achieve a value which surpasses this 2, and it goes up to 2 root 2. That means we are in a position where I can have an advantageous use of this quantum entanglement in any kind of information processing processes. So that means it was shown by this particular game that if you have a correlation which is even stronger than the classical correlations that you can think of, in this case it is entanglement, then you are able to surpass a certain value. So that means people then started to believe, okay, quantum theory can give me some kind of resources which are not possible classically. So right now, that means what we have over here, we have identified that quantum entanglement is a very strong form of correlation that we need to understand. And if I can harness this resource, I can use this for a very, very significant advantage in communication protocols and in computational tasks. So the idea is then, if you have such a quantum entanglement, how do you define it mathematically? Now, why this mathematics is coming over and over again? Because as I told you that it is always, the thing is that this language of science is written in the language of mathematics. So if we have to go and if you have to define something, first we have to go through mathematics. That is, what are the things that we can do with this entanglement? How actually entanglement is defined? If I give you a particular state, then whether you are able to detect that, okay, you have indeed an entangled state or not. So those are the things that we should understand, and to understand that, we need those kind of mathematics. We need to understand where does the state is there, what are the states looking like, how do you say that a particular state is entangled, and then what we can do with that entanglement that we have with us. So for that, now I am coming to the screen. Okay, so I am sharing my screen now. Okay, so I hope this screen is visible to all of you. Fine, good. So what happens is that, as I said, that there's this whole quantum world where we can actually explore certain things which can never be explored in the classical scenario. So there's this thing which this picture actually depicts, and people found it to be very interesting. People found it to be very exciting. And in fact, this was actually in the early 1980s when this famous scientist, Professor Richard Feynman, came with this idea that why not you use quantum mechanical principles to do information processing and to do computational tasks. And this actually broke open this vast area of quantum information and computation. Okay, so then what were the main ideas? The main ideas were, like, Einstein thought that this is kind of a very spooky action at a distance. This is nature of entanglement, because what is happening over there is Alice is doing something on his particular particle, and that is having an effect on Bob's particle. So that's why he termed this as a kind of a spooky action at a distance. And then this term entanglement was first coined by Professor Schrodinger, who used this term entanglement for the very first time. And then, as I said, that the early 1980s, Professor Richard Feynman came with this idea that why not use quantum mechanical principles to study quantum information. That means whether we can use those principles in order to see what advantages we can get in information processing protocols as well as computational tasks. Okay, so this was something that I told you, that what actually is information. So this information is something which is a kind of news or knowledge which is received or which is given. So let me see this very intuitively. Like, for example, you are reading a detective story, and when you are reading that detective story, of course you are in the first few pages, so you don't know who the culprit is. So somebody who has, suppose one of your friend has already studied, already read it, and suppose he comes to you and he wants to be a spoiler, and he comes to you and says that, do you know who the culprit is? The culprit is this. Now you might be like devastated by knowing this, because you thought that you should read the story and you should know who the culprit is, but he has been a spoiler. But at this particular moment, he has indeed given you an information, because he told you something that you didn't know. So he has given you some information. But suppose that you had already read that book, that detective book, that story, and now suppose your friend comes and tells you that he is the culprit. So then what happens? Is he giving you any kind of information? No, he's not able to give you any kind of information, because you already knew that who the culprit is. So if suppose you already have a news of something, you already have a knowledge of something, then of course you are not getting any information by knowing it, by learning it. So that basically is the essence of information. And when you pass this information in the classical scenario, as I said, that what you do is that you pass it through a strings of zeros and ones. That is what is depicted by this particular figure. Okay, now this was, as I said, that he is considered Professor Claude Shannon, who is considered to be the father of information theory. And in his 1948 paper that came in the Bell Technical Journal, he actually gave two very profound principles on information processing. And those two profound principles on information processing was the source coding theorem and the channel coding theorem. Because what happens is, like, when you have to pass an information from the source to the destination, when you have to do that, then you have to do some coding. That means do some coding in the sense that you use the minimal number of resources. So what can be that optimal coding? It was Professor Shannon who showed this. And then when you transmit information from one place to the another, what you need is a channel. And that channel also has to be very efficiently used. So what can be that efficient use of that channel? That also was laid down by Shannon in that particular paper, which goes by the name of this channel coding theorem. So this particular picture actually shows you that what happens in a communication system. That is, you have a information source, you have a transmitter, you have a channel. And as you can see over here, what happens in this channel is that sometimes, and in fact not sometimes, I should say most of the times, that this noise comes into that channel. So what happens when somebody receives a particular message over here, then that particular message might be distorted. So then what you have to do over there is you have to use some kind of an error correction scheme so that you can get a legible, legitimate message and you can read it. So you have to apply some principles of error correction. So this is giving you a holistic view of how the model of a communication system looks like. So then what is information? Because see, like for example, if you are going to a shop and you want to buy some rice, then when you go to that particular shop, what will you say? You will say that give me 1 kg or 2 kg or 3 kgs of rice. So suppose you are going to a shop which sells information. So when you are going for that and you want the shopkeeper to give you something, so you have to quantify it. So how does this quantification of information take place? So this quantification of information actually takes place with the help of this thing, which is known as the Shannon entropy. Now, as you can see that this Shannon entropy is what? You have this quantity log px, you are multiplying with px, and you are taking the negative sign. And rather if you come to this one, because if I take minus over here, then it will become log of 1 by px. So if you come to this particular position, then what happens? What is this factor? Log of 1 by px. So suppose this x is a kind of a random variable, that means you don't have the complete information about that, you don't have the complete knowledge of that. There is some sort of a randomness over there. So what happens is that what happens over there is that in that particular case, this 1 by px, so suppose you have a very high probability of knowing it. Okay, so what will happen to this 1 by px quantity? So if you have a very high probability of of that knowing it, 1 by px will be very less. And if you have a very less probability of knowing it, then 1 by px will be very large. So this quantity that you have over here is known as the information content. And what is this Shannon entropy doing is, it is calculating the expected value of the information content. That means what you are doing over here is you are multiplying this quantity by the respective probability and you are summing it up. And this is known as the Shannon entropy, which measures quantum information. So this actually shows, in case of a binary probability system, that these probabilities are plotted over here, and this is the corresponding entropy, the Shannon entropy. And as you can see that when p, that is the value of the probability, is equal to half, then you have the total randomness, or rather we should say it in this way, that we have the maximal randomness, because over here the Shannon entropy is highest. Because if suppose I say that you have a particular Okay, so now is the screen visible? Can please anybody tell me from the chat, is the screen visible? Can somebody please tell me in the chat that whether the screen is visible or not? I think the screen is visible.
Sir, some students, they are mentioning that the board is not visible to them while writing.
Okay, yes. So right now I am not doing anything on the board right now. I am doing it on the screen.
No. When you were writing, they said the same. That's the reason.
Yes. Now the screen is okay, na?
Now it's okay. When you are writing, just zoom it to that place, sir, so that they can.
Okay, fine.
Right.
Okay, so you have this total randomness over here. So when is this total randomness coming? This total randomness is coming when we have that p is equal to half. So that is the maximal randomness that you have over here. That is the graph of the Shannon entropy. Okay, so then what about quantum information that I was talking about? So quantum information is the information of the state of a quantum system. Quantum information can be processed just like you can process classical information, and it can be analyzed with mathematics and computer science. And it can also be transformed and handled with the help of quantum algorithms. That means it works on these quantum states. Okay, so this is something which are the units of information. So what is the unit of information when we have the classical system? So the unit of information when we have in the classical system is that we have this thing that is known as bits. These are the bits over here. So what does this? So the tail over here represents a 0 state and the head over here represents the 1 state. So these are bits. As I said earlier when I started my lecture, that when you have a classical system, then you work with bits. So when you work with bits, then the system can either be in a state 0 or it can be in a state 1. So that is known as the classical bit system. But then when you move to the quantum system, this is the situation that is happening. That is, now when you are moving to the quantum system, then it is not that only you have a 0 and you have a 1 over here, but you have a combination of 0 and 1. And this particular combination is known as the linear combination. So it is feature something like this. That means, see, when you are tossing a particular coin, when it is falling on the ground, then either you have a 1 or you have a 0. But what this picture tries to depict is that in this particular picture, it can be anything between 0 and 1. So this picture actually tries to tell you that how actually qubits can be visualized. That means qubits are something which are represented by this mathematical notation, and this is the thing that we are getting over there. That means it can be in any possible combination of 0 and 1. So this is the thing that is the classical system or the classical bits. It can be whether in 0 or 1. So what I need? I need a state, I need a system. So in that particular system, what happens is either I can be in a state 0 or I can be in a state 1. So one such physical system that you can think of is this on and off switch. So when you have this on and off switch, so either you can be on this or you can be on this. And now when you are coming to this, that is in the qubit system, that is in the quantum system, then what you can have is you can have a possible superposition of this 0 and 1. And what can be such systems which can allow you to do so? The systems can be any quantum 2-level system that can act as a qubit. For example, atoms, for example, spins of the electrons. We know that electrons do have a spin, and when you represent a spin, you can be spin up, it can be spin down, and when you are doing this, it can be any spin between them. That means any possible combinations of zeros and ones. So if I can exploit this kind of states, if I can use them in information processing, you can realize that what is the significant advantage that we are getting out of it. So moving now, so this is how the quantum bits are represented. So like imagine that you have a sphere like this, where you have the y, x and the z axis. So this top over here represents 0 kate, that is the 0 state. This is this vector. And over here minus z represents your 1. So this means this represents your on, this represents your off. And as I said, that it can be in a possible combinations of any this 0 and 1. So that is a0 plus b1. So any vector pointing to the surface of the sphere is a valid quantum state. So it can be a vector like this, it can be a vector like this, it can be a vector like this. Any vector pointing to the surface of the sphere is a valid quantum state. And so the quantum states can actually be represented by this. So I hope in the previous sessions you have seen that these quantum states actually belong to a particular space which are known as Hilbert spaces. This is what you have seen in the postulates of quantum theory when you learned about that. Okay, so this is the representation. That is, I will represent this spin up by 0 and I will represent spin down. These are some of the languages that I am using. There is nothing like very special about this language that I am using. You can just think of that these are two states. One is this 0 state and the other one is this 1 state. And I am using a kate symbol for that. So when I am using the kate symbol for that, what does it mean is, it means that over here in this particular case, it represents a matrix. So what kind of a matrix it looks like? Let me show you. Okay, just give me a minute. Okay, fine. So what I am doing over here is, you think about something like this. You have this 1 0. So this is my 0 state. And what is my 1 state? So this is my 0 state. And what is my 1 state? Is did somebody say something?
Sir, make it as a full screen, sir.
Is it okay now?
You make the presentation as a full screen.
Yes.
It looks clear. That's all. It's okay, sir. It's okay. It's okay.
I'm using Microsoft Edge for this. Okay. So, okay, now is it okay?
Now it is okay, sir.
Okay. And
Done.
okay, so what I'm using over here is I'm using the problem is now I'll not be able to work with it. Okay, just give me a minute. That is happening actually when I'm using this.
Sir, you can carry on how it is feasible with you.
Yes.
No problem.
So this is the thing that I am working on. So one is 0 1. This is the column matrix. So this represents 0 1. So then what will happen to this alpha 0 plus beta 1? So this alpha 0 plus beta 1 will look like alpha into 1 0 plus beta into 0 1. So that means it will be alpha beta. So this will be a general single qubit state. That means when just I am thinking about one system. Okay, so as I said that these are the corresponding matrices and this is how it looks like, and all of these states, as you have seen in the postulates of quantum theory, that live in a Hilbert space, which is a kind of special kind of a collection of vectors. And see, so this is this quintessential and very like what should I say, the most iconic figure that you have for superposition, which actually was proposed by Schrodinger, and you go and you know by this name of Schrodinger's cat. That means you can have a state which can be in the superposition of two states. So this is that state that they are thinking of. That means you can have 1 by root 2 0 plus 1 by root 2 1, the superposition state. Again, this is something which is not allowed in the classical theory. Superposition. So superposition, you can say that superposition is one of the fundamental resources which is only quantum theory is allowing you to use. Classical theory, no. Okay, now we come to 2 qubits. Why I am coming to 2 qubits? That means why I am having this 2-level system? I am having this 2-level system because if I have to define entanglement, then in case of an entanglement, I need a 2-party system. At least 2 parties should be there. So if 2 parties should be there, that means now I have to move from the level of a single qubit to the level of 2 qubits. So then how do I define these 2 qubits? So this is how the 2 qubits are defined. That is, now I am taking the help of an operation which is, the name is tensor product. So I am taking the product between these 2 vectors, and these are my possible states: 0 0, 0 1, 1 0 and 1 1. Now see, this is also happening in classical systems also. In the classical systems, you can say that, sir, when I am having a 2-party system, then you can say 0 0, you can say 0 1, you can say 1 0, you can say 1 1. You can have these 4 possibilities over there. But right now what I am saying that you can have a possibility of this type: alpha 0 0 plus beta 0 1 plus gamma 1 0 plus delta 1 1. You can have a system like this. So when you have a system like this, that means you can have a possible combination of all of this over here. These are known as basis vectors. That means any vector psi in the 2-qubit system can be expressed in this particular way. And as I said, what you should have: mod of alpha square plus mod of beta square plus mod of gamma square plus mod of delta square should be equal to 1. So that means in a 2-qubit, this is how you can represent a 2-qubit state. Similarly, if you move to 3 qubits, that means now you have 3 parties. Then what you can do? You can represent a state in this particular way. And see, these are your different coefficients over there. And please remember that they should obey this restriction. That is, over here in this case, it will be mod a square plus mod b square plus mod c square. In this way, up to mod 8 square should be equal to 1. Fine. So now what happens is, Like when you have a quantum state, then there can be two kinds of quantum states. What are the two kinds of quantum states? The two kinds of quantum states is that you can have a pure state and you can have a mixed state. So see over here, when you are talking about a pure state, then a pure state means simply a vector like this. But when you are talking about a mixed state, then what happens is that you can take this state and you can take another state, and what you can take is you can take a possible mixture of these two states. So this P denotes probability. That means you have taken P of this, you have taken 1 minus P of this, that means you have created a probabilistic mixture, and this is the state that you have. Now here in this particular case, I have just taken the example of a single qubit state, but this can be easily generalized to any number of states. So this is the basic notion. The notion is that whenever you have a vector, I just have a vector. So whenever you have a vector, then that actually represents a pure state. But if there is a quantum state which cannot be represented by a vector, that is most general, and in a short while from now we will try to see that how those kind of quantum states are represented, and those are actually represented by something which is known as density matrices. So what we will see over there is that it is the most general description of a quantum state. That is, given a quantum state, how do you represent it mathematically? So this actually gives you this notion of pure states and mixed states. Obviously, see what happens is why this question of mixture is coming. How do I intuitively understand this, and not just only mathematically? It means that like you have a state psi, you want to keep it in psi state, but the problem is there will be environmental interactions. You cannot just keep that state psi completely isolated from the environment. Since you cannot do that, some kind of a noise will creep in, and basically this mixture or this mixed state brings that motion. That is, you wanted your state to be in a very pure state, but you are not able to use it because, as I said, that there may be lots of reasons for which the state interacts with the environment and the state is no longer in the pure form that you want to get it. It will be in a mixed form, and that particular mixed form is this. So that's why there is this distinction between what is a pure state and what is a mixed state. So although we want the states to be pure, but when we actually work with them, it might be mixed. And that's why, as I said, when I was showing that, although I was showing it in the context of classical information theory, that you have a channel over there. So you wanted that there's it should go, and whatever the sender wants to send, the receiver will receive it. But the problem is some noise will creep in. And that is why this mixed states idea has come into the picture. We have to incorporate it, otherwise we will not work with it. Okay, so as I said that means now at this particular moment, what I need is, I need that how do I describe a quantum state with the help of a density matrix. So this is how the density matrix representation is done. That is, suppose I have taken a state like this, and I have taken another state like this. If the mixing parameter P is 1 by 4, so P times this thing and 3 by 4 times this thing. So see what I have done over here is, this is something which is known as the outer product. This is again a representation of this outer product, means this is the quantum state that I am looking for. Now see, this state that you have over here, you can never express this state as something like some phi. That means in the form of a vector, you will not be able to express it. So that is what I said, that whenever you are able to represent a quantum state in this particular form, then that particular form means that you are using a pure state. Otherwise, you are using a mixed state. So this density matrix is the most general formulation, because even if it is a pure state like psi 1 over here, suppose this one, this is a pure state. So what I can do is that I can take psi 1, and this will be my density matrix rho 1. Similarly, my density matrix for rho 2 will be psi 2, and I'll tell you what does this mean. This is the outer product. So then what I am doing over here, I am taking a mixture of this. That is, I am taking 1 by 4 times this plus 3 by 4 times this. And this is in the matrix form. So see, these are my outer product, 0, 0. So 0, 0 looks like this, 1, 0, 0, 0. 0, 1, this, 1, 0, this, 1, 1, this. These are the different things that I have over here. Okay, so now what happens is that if you look at this, my state over here, so this is a representation of a density matrix. So see, this is your 0, 1, 0, 1. And this is how the density matrix looks like. And remember that trace of this density matrix. So what is the trace of a matrix? Sum of the diagonal elements. So that trace will be equal to 1. Okay, so pure states, as I said, can be represented by state vectors, but mixed states cannot be represented. Now, one of the most important feature of a quantum theory, that is measurement. Now, what is this measurement? See, suppose you have walked into a room and there is a flower stand. And when you walk into that room, I ask you that what is the position of that flower stand? What will you do? Some light gets reflected from that flower stand and you observe that, okay, the flower stand is over there. So that means what you have done is that with the help of the light which gets reflected from the body of the flower vase or the flower stand, you are saying that that is the position of the flower stand. That means what you have done over here is you have done some kind of a measurement. Measurement of what? Measurement of the position of that flower vase or that flower stand. That is what you do. Now see, in this particular process, although when you do that, this is quite obvious to you, that when those photon particles, that is light, is like hitting that flower vase or and that stand, and you are able to make some you are able to say that, okay, this is the position of that particular flower vase or that flower stand, then you already know that like photon particles will never disturb the position of that flower vase. That means it is getting reflected, so it does not mean that it changes the position of the flower vase. The flower vase remains over there. No questions about it. So you did some kind of a measurement and you said that, okay, the flower vase is over there, the stand is over there. Very good. So now that was a very like macroscopic object, classical system. Okay, done with that. But as we have seen, that quantum theory means that we are working with electrons or atoms or something like that. So obviously electrons and atoms are not moving in front of my eyes. Okay, so I will say that, okay, see, that electron is over there or that atom is over there or this is there. I cannot do that in that particular way. Those are not macroscopic objects. So then what I have to do? I have to do some kind of a measurement. So suppose I want to know the position of an electron. So the position is mentioned by a state. Okay, and when it is the position is maintained by a state, then that means it can be in any possible combinations of zeros and ones, alpha 0 and beta 1, and I want to know the position over there. The problem over here is that again I will need some kind of a measurement to do. So if I have to do that measurement, what happens over here is that since those things are very delicate to handle, think it in this way very roughly, what will happen is that that measurement will disturb the state of that system. And what will happen is that although it might be in a superposition state, but when you actually measure it, you either see it as a 0 or you see it as a 1 with some probabilities. So what happens is, like whenever you have to learn something from a quantum system, the quantum system or the state is actually storing some kind of an information. But when you have to learn that information from it, you have to do some kind of a measurement on that particular state. But measurement will disturb it. And that's why what will happen is you either get the output as 0 or you get the output as 1 with a certain probability. Again, this is something that you have learned in your postulate. And as you can see that probability, as I said, these are the probabilities. So what will happen? Probability of alpha square plus probability of beta square, sum of all the probabilities will be equal to 1. So what happens? You have this state, this is your measuring device, you are doing this, and then you are getting the output as this one, and you are getting the output of this one. And this probabilities that you are getting is coming according to a rule which is known as the Bond's rule. So whenever you do this, that means what you have to do over here is that you have to do some kind of a measurement. That is very, very important. Because in classical systems, it was quite obvious to me. Where is that boy? Or what is the speed of that person, the velocity of that person? These were very easy questions to answer. And I know that while answering this type of questions, my way of measurement, my way of observation will never disturb the state of the system. I was very, it was so sure about that it seemed to be very obvious. But this is not quite obvious in quantum theory, because we are now dealing with a very, very counterintuitive phenomenon which actually is not happening in our day-to-day lives. Okay, so now again, this was for a single qubit system. Now this is for a 2-qubit system. So what we will see is that this kind of a 2-qubit measurement will be put to use in this teleportation when I tell you. This is a very, very interesting communication protocol which I will tell you where we have to use quantum entanglement. So now coming to quantum entanglement. Okay, now look at this particular state. Let us understand that what is actually this phenomena of quantum entanglement. So suppose I have a state in this position. That means it is a composite system, that is a two-party system. And as you can see over here, 0, 0, I can very easily write this as 0 tensor 0. That means it is factorizable. I can factor it. Suppose I had a system like this. I can very easily write this as, let me take out 0 from here, tensor product 0 plus 1 by root 2. So see, again this is a state, this is a state, and I can write this state as a factor of this 2. I can write it in this particular way. So this is again factorizable. But look at this state over here, this state. So what is this state? This state is 1 by root 2, 0, 0 plus 1 by root 2, 1, 1. Now if you look at this particular state, are you able to factorize this? You will see that no matter how much you try, you will never be able to express this particular state as some state psi tensor another state phi. You cannot do that. You cannot write it in that particular way. You cannot do that. Okay, so what does this actually show? This actually shows that yes, this is a question that whether we can incorporate quantum field theory into quantum information or not. But yes, people are trying to exploit this kind of features, and they are trying to see this thing. But right as of now, to the best of my knowledge, I don't have any information like any substantial thing has been done over there or not in this thing. In fact, this idea of quantum information and quantum computation, people are also trying to use to understand black holes. Okay, so that is another very important area of research that right now people are working on. But as I said that yes, to the best of my knowledge, I have not seen any like substantial work on the relation between field theory and quantum information. Okay, so as I was talking about, so what we have over here is I have this entangled state. Why am I calling this entangled state? Because it is not factorizable. It is not factorizable. That means I cannot break it up into the product of tensor product of two states psi and phi. So I will call this not factorizable. It means I will call it to be entangled. Now here lies a question. The question is that, sir, what you have showed over here is that if you take a pure state, then for that particular pure state you are telling me when it is entangled, when it is not. But we know right now that states might not be always in its pure form, might be in a mixed form. Then in that case, how do you define entanglement? This is the the most important question in quantum information theory. That is, if suppose I have a mixed state, then how can I define entanglement over there? This notion of factorizability comes over there. How? What happens is that suppose I have a density matrix rho, which is a mixed state. As I told you in my previous slide, that rho represents a density matrix. That means it represents the most general way of depicting a quantum state. So it's a mixed state. And suppose this rho that I have over here can be written as in this particular way. For some I, pi, some rho ia, tensor rho ib. So that means what I am doing? I am taking possible combinations like rho 1a, rho 1b, then I am taking rho 2a, rho 2b, and what I am doing? Multiplying this by p1, multiplying this by p2, and I am adding it up in this particular way. If I can express this rho in this particular way, then it will mean that this rho is separable. That means it is not entangled. It is not entangled. So if there is a rho which I cannot express in this particular way, then that will mean that that particular rho is an entangled state. So that means, like when you talk about quantum entanglement, for pure state this is something that we can see, but for mixed states this is how the general definition is. So this actually is brought about over here. That is, let H denote a Hilbert space. So what was that Hilbert space that I talked about? This Hilbert space was that it is a special kind of a vector space, and what this Hilbert space do is they actually tell you a way that in a particular vector space, when can we say that two vectors are orthogonal to each other? Okay, so this actually generalizes this notion of orthogonality. Like you have worked with vectors, like you have a vector, b vector, then what do you do over there? You say that two vectors are orthogonal to each other when a dot b, that is when you are taking the dot product, becomes equals to 0. So over here also this Hilbert space actually generalizes this notion of this the dot product. That means it says that in case of any other object, and not necessarily they are those physical vectors, when can you bring in this notion that they will be orthogonal to each other? So that is why that in the postulates of quantum theory that you have seen in one of the previous sessions, it says that the states live in a Hilbert space. So what happens is that we are saying that let H denote a Hilbert space, and let us take a pure state psi which belongs to that H. So H is a collection of those pure states, and suppose what I do is that I take psi A belonging to HA and psi B belonging to HB, where HA and HB refer to the subsystems. Okay, so whenever you are taking up a state, that state is coming from some space, some Hilbert space. You are taking up another state coming from some other Hilbert space. They may be same, they may be different. So what happens is that if you can write this psi as the tensor product of this psi A and psi B, then we will say that this psi is separable. Otherwise, we will say that it is entangled. So this notion, as I was talking about, that when you move to a mixed state, this is how it generalizes. That is, what you do is that you take a combination, which combination is known as a convex combination. Why convex combination? Because what happens over here, if you look at this particular way of writing it, then these are the probabilities. So you are taking a combination where each of the weight factors is a probability, and we know that sum of all the probabilities is equal to 1. So this is why this is known as a convex set, or a convex combination rather. So it is known as a convex combination. Just a minute, there seems to be another question. Yes, of course, there is a significant relationship between mathematics and quantum information. Why I am saying that this is the relationship? Because see, as I was telling you, that whenever you are doing any kind of a trying to understand any kind of a scientific phenomena, then it is not just only that you do experiments and you see those things. It has to be formulated. It has to have a language. Language of science is actually mathematics. Now the thing is that what kind of a tool you will use. Like for example, let me tell you about dynamical systems. So when you are working with dynamical systems, or in fact, just take the Newton's laws of motion. So when you are taking the Newton's laws of motion, if you look at the second law, then what does it say? That force will be directly proportional to the acceleration. That means we get that force is equal to mass into acceleration. Now when you are getting force is equal to mass into acceleration, then we know that if x is the displacement and t is the time, then the second derivative of displacement with respect to time gives you the acceleration. And suppose I take that mass to be constant. Okay, so force is what? Force is mass into the second derivative of the displacement with respect to time. So what is this kind of an equation? This kind of an equation goes by the name that it is a differential equation. So that means if I have to study laws of motion, then I have to take the help of differential equations to do that. So if I utter this word, that force is mass times acceleration, then you have to represent it, isn't it? And that representation is through a differential equation. So what does that differential equation do over there? That differential equation is actually giving you the language by which this second law of motion can be written. That is giving you that language. So over here also, when you talk about quantum information, what happens is that we look for tools that which can help us to understand quantum information in what language it has to be written. So at the beginning, if you notice, I told you that when you do or study this quantum information, you need to have this idea of what is a linear algebra and what are probabilities. And why this is important, it is not only important that it gives you the language, but it also actually tells you that if you have some ideas over here, that means some manipulations or some theorems or some new results in linear algebra and probability, then you might be able to use that over there in case of quantum information. So things are interlinked. Things are interlinked like this. You cannot write down anything without mathematical equations. So when you have that kind of a thing, what happens is that you are trying to have a language, and if there are certain things that you can do in that language that can have a profound effect on that application. So that is how you look at it. Because as I said, you are not able to see electrons, you are not able to see the spins of electrons. So if you have to have some idea about that, you have to go through the language of mathematics. Okay, so that is something that one can say over here. Okay, thank you very much for bringing up this question. Good. So see, this actually gives you a very a picture that there will be a source, and unless and until there is a source, there cannot be any correlation between these two, because somehow or at some point of time, it may be very long back, those two particles might have interacted with each other and they have separated out. One has gone to Earth and the other one has gone to Mars, and they have separated out. But since they had interacted long back, they have some kind of a correlation between them. And we are trying to see whether that correlation is an entanglement. So what happens in case of an entanglement is that it cannot be written as a tensor product, like this, as I said, as I was showing you in that mathematical explanation. But separable states, it can be written in the tensor product form. Okay, so there seems to be another question. Let me see. Yes, this is the thing that I just told Miss Priya was there. She asked me the same question, that whether there is any relationship between mathematics and quantum information, and the same question. So that is what I said, like what is the relation between these two. So all these things are interlinked with each other. We are just trying to see what are the relationship between.
So same question asked for more time. So if the same question is rises, they're sending in a single question only, as a single question. Right.
I just want to see that what is the relation.
No problem, sir.
Okay, now let me give some illustrations of it. Let me give you some examples. So what are the examples? Already I told you about this particular state, that is 0 0 plus 1 1 by root 2, which belongs to a 2 qubit system. The state is entangled because you can never write this state as a product of two state vectors like this. That's why I will call this state to be an entangled state. Now this, see, in a 3 cross 3 system. Okay, now what is a 3 cross 3 system? See, when I was talking about a qubit system, when I'm talking about a qubit system, then the two of the basis vectors that I have over there is, I have this 0 and the other one is 1. And I am expressing any psi over there as A0 plus B1. I am writing it in this particular way. So these are the basis vectors. You give me these two blocks, I can represent any state in a qubit system. Now then, if you increase the dimension, if I go to a qubit system, what will happen in the qubit system, that is a 3-level system, is that I will have 3 basis vectors, 0, 1 and 2. That means now a state psi over there can be represented as A0 plus B1 plus C2. See, I am using 3 basis vectors, 0, 1 and 2. So if suppose now I have a 2 qubit system, so if I have a 2 qubit system over there, then what are the possibilities? I can have 0, 0, I can have 0, 1. In this way, I can have 2, 0 and I can go up to 2, 2. So these are the 9 possibilities that I will get over there. So in a 2 qubit system, any state can be represented as a possible combination of this 9 of them. These are the basis vectors over there. So in a 3 cross 3 system like that, that means when Alice and Bob is sharing a state where each of their levels are 3-level systems, that is spanned by 0, 1 and 2, then I can take these vectors from there. I can take the vectors from there and then I am forming a state like this. So see, this is an example of a mixed state, because what I have done, I have taken combinations of these states. So this is an example of a mixed state, and this particular mixed state can never be written as the convex combination of separable density matrices. That's why I will call this state to be entangled. So this is an example of a pure entangled state. This is an example of a mixed entangled state. Okay, and these are the famous examples of an entangled state in 2 qubit system, and this is the Bell state. In fact, if you go back and try to recall the first game that I did with you, the game which I told that if you allow some kind of quantum resources to share between Alice and Bob, then you can go up to the value of S to be equal to 2 root 2. Basically, that can be achieved. That value of 2 root 2 can be achieved by this kind of states, which are maximally entangled states. And why they are known as maximally entangled? Because in the 2 qubit system, they possess the maximal amount of entanglement. Nobody can have an entanglement more than this. That is why they are known as the maximally entangled state. And in that particular game, only these states can give you that value of 2 root 2. You can have other entangled states, but they can give you a value greater than 2, but they will not be able to give you a value of 2 root 2. Only these states can give you that. So as you can see that in a communication protocol, if I allow Alice and Bob to share a state like that, then in that particular state, when I give a maximally entangled state to share between them, then of course Alice and Bob can exploit that and get a very good communication protocol. They will, and what they will want in an ideal scenario. In the ideal scenario, they will ask and they will want that the state that they are sharing between them is a maximally entangled state in the ideal case. And why I am saying ideal case? Because I said that there is a lot of environmental interaction, and due to that environmental interaction, the state doesn't remain in the pure form, it gets into the mixed form, so I have to work with a mixed entangled state. It is not that I'm having this very good fortune of working with the maximally entangled state. And this has another name, and that another name is Bell states. Now actually that the game that I told you, just excuse me for a minute. Okay, so this game that I told you, that particular game is known actually as the Bell game, because it was Professor John Bell who actually showed that this kind of states can give you a value of 2 root 2. And that goes by the name of Bell's theorem, though it has far more far-reaching consequences than what I'm talking about. It has many far-reaching consequences, and actually Bell's theorem has been used right now to in this cryptographic schemes. So that is a different question altogether, but it was because of him that we came to know about this power of this maximally entangled states, which are also known as the Bell states. And as I was telling you earlier, that when you move to a 2-qubit state, then your possible basis vectors are 0, 0, 0, 1, 1, 0 and 1, 1, cake. But those are not only the basis vectors that you have. In fact, whenever you have a vector space, then you can have an infinite set of basis vectors. The only thing that will be common to all of them is that they will contain the same number of basis vectors. So in case of the 2-qubit system, just like you had 0, 0, 0, 1, 1, 0 and 1, 1 acting as the basis vectors, this can also act as the basis vectors. And that basis vectors is known as the Bell basis. So they are forming a basis. They are forming a basis because you take any 2-qubit state psi, they can be represented as a linear combination of this one. That's why they are talking it as, they are saying it to be the Bell basis. Okay, now detection of entanglement. As I said that, okay, you have identified that, okay, entanglement is something that I cannot have in the classical theory. It is giving me a correlation that is not possible in classical systems, and you have defined entanglement. Now suppose you imagine this situation. Okay, so you imagine this situation that I am giving you a composite system. I have given you a state, and then I am asking you, okay, tell me whether it is entangled or not. Then there is a problem. The problem is your definition has told you, so you have to now see, okay, I have to see that, okay, there are separable density matrices, and I can write the state that has been given to me as a convex combination of this, and then I will say that it is not entangled. So suppose you take a possible combination and see that it can be written as this combination. So if it can be written in this combination, directly at that moment you will say that, sir, this is separable because I can write it as a convex combination of separable states. But suppose those possible choices that you had made doesn't work out. That means you are not able to write this one as this combination. But will that mean that it is entangled? No. There might be some other choice. So you have to bring in another choice and you have to see whether you can write it as a possible convex combination or not. Again, suppose that also fails. Again you have to come up with some density matrices, again you have to check. So that means what? That you have to do this, go on, you have to go on doing this till you get, you never find it. So that means this process, the definition, what the process says, is actually not giving you a very constructive way to say that whether a particular state is entangled or not. You need a constructive way, you need a criteria to say or to tell whether a particular state is entangled or not. That criteria you want to know. So right now we will see one such criteria. So before that, let me see, there seems to be a question. Yes, communication is possible with entanglement. It is indeed possible. That is why I will go and I will say that about teleportation towards the end of my lecture. Okay, that how this entanglement can help you to actually use something which is known as the teleportation protocol. And by using this teleportation protocol, you will be able to achieve something with a higher fidelity than what can be allowed in a classical system. So entanglement can be used for that particular purpose. Okay, so what happens in this partial transposition, this positive partial transposition criteria? So in this positive partial transposition criteria, what happens is that suppose a row is written in this particular way and you partially transpose that particular matrix. So partial transposition means what? Like I said that whenever you have a two-party system, that is Alice and Bob system, when you do a total transposition, it means that you know how to transpose a matrix. Okay, that means you change the rows to columns and columns to rows. But what happens in case of the partial transposition is like you keep the system at the Bob's end intact and you just transpose the elements of Alice. So that is known as a partial transposition. Similarly, you can keep the system Alice's system intact and you do only the transposition in the Bob's system. So that actually is represented by this mathematical form where I have done the partial transposition with respect to the Alice's system. That's why I have represented it rho TA. So any bipartite separable state rho has a positive partial transposition. That means rho TA will be greater than equal to 0. Can anybody tell me at this particular moment, what do I mean by a statement like this? This is a matrix, I am using a symbol like this greater than equal to 0. Can anybody give me some idea about how am I doing this? Anything, you can write it in your chat box and tell me. Just I want to make this a little bit more interactive. Can you tell me what is this, the meaning of this thing? Anybody? Okay, actually what happens is that in case of a matrix, when I write something like this, it means that, okay, let me see, somebody might have answered. Okay, so what actually do you mean by quantum state complexity? I'm not getting your point because there can be many kind of complexities that you can think of. Like you can have a computational complexity or any other complexity that you can think of. So what you say in that quantum state complexity, first we should be like agree on what kind of a complexity you are talking about. Then I think I might be able to answer that particular question. Okay, so when I'm saying that A is greater than equal to 0, what does that mean is that A will have all non-negative eigenvalues. That means all the eigenvalues that A has will be non-negative. So if I see that I have taken a partial transposition and after taking partial transposition I find that A remains in such a way that all its eigenvalues are non-negative, then I can say that this state rho is separable. So look at this. So please, just I want to make a correction. This is not the correct statement to make. The correction is that if there is a bipartite separable state, then it will have a positive partial transposition. If I get a negative partial transposition, that means it will indicate that the state that they have is having some sort of entanglement between them. But there is a warning. And what is that warning? That warning is that sometimes, look at this thing very, very carefully. I said that when rho is separable, then it will have a positive partial transposition. But it can happen that there is a rho which has a positive partial transposition, but it is entangled. So that means the converse of this statement is not true in general. That means if it is separable, it will have a positive partial transposition. But if it has a positive partial transposition, it might not be separable. So, but what I can at least be sure is that if it has a negative partial transposition, then I am sure that it is an indicator that the state that Alice and Bob is sharing is entangled. I can say that. I can detect the entanglement in that way. But as I said, that if suppose I test and I find that the transposition is positive, inconclusive. I cannot say anything. So if you look at this, this is an illustration that this is a famous quantum state, that is the Warner state. So where you have this chi plus to be equal to this, and x lies between 0 and 1, and I is the identity matrix. It can be easily verified if you like take the partial transpose of this, then you will see that this partial transpose will contain negative eigenvalues whenever x is greater than 1 by 3. So this particular state is entangled when x is greater than 1 by 3. Otherwise, it is separable. And as I was telling you, this is the example that I had shown you in one of these slides, that this state is entangled, but it has a positive partial transpose. Remember, this is a state that we were having in 3x3 systems, that is 2-cuplet system. This is one of the most counterintuitive features in the detection of entanglement. That is, what happens is, like when you have a particular entangled state in higher dimensions, in like 3x3, 4x4, something like that, then it may happen that those entangled states has a positive partial transpose. So this state that I had taken the example of, this is the example of such a state, which although entangled, it has a positive partial transpose. Now that means that there is a very interesting feature, interesting theorem which goes by this thing, that is known as the Perez-Horodecky criterion. And this Perez-Horodecky criterion says that if your state is in 2x2 or 2x3 or 3x2, then in these dimensions the partial transposition criteria is necessary as well as sufficient. That means over there this particular statement will hold both ways. That means if a state is separable, then it will have a positive partial transpose. If a state has a positive partial transpose, it will be separable. That is necessary and sufficient in 2x2, 2x3 and 3x2 dimensions. But the moment you move to a different dimension, then what happens is that this is no longer true from that side. That means there can be entangled states which has a positive partial transposition. So see, this criteria has a limitation. In fact, this is one of the most important open problems in quantum information theory, that actually there is no universal criteria by which you can say whether a particular state is entangled or not. And this is known as the separability problem. Now there is another way by which I can test whether a particular state is entangled or not. What is that test? So to understand that test, let us see a convex set. As I was talking about, I was taking convex combination, suppose I have some objects like O1, O2, and I'm taking this thing where summation of pi is equal to 1. So this is a convex combination. Now what happens in a convex set is, like as you can see over here, if I take 2 points over here and if I join them by a straight line, this straight line will entirely lie on this set. That is why this is known as a convex set. But suppose I have this thing. So this is my, suppose my region. So I take a point over here, I take a point over here, and I join them by a straight line. What will happen? Some portion of the straight line will not lie in the region. That means this is not a convex set. So there is a very important theorem in mathematics that goes by the name of the Hahn-Banach theorem. And this Hahn-Banach theorem tells you that if suppose you have this a set which is having this property, that means it is convex, and there is another property which is known as closed. If a state has these two properties, if a set has these two properties, then what you can do is that you can distinguish any point which is outside this state, outside this set, by this hyperplane. So when you can do that, this one is actually known as a witness. What will happen in case of a witness is that when we talk about these separable states, the separable states actually form a convex and a closed set. That means all the points over here will form a closed and convex set. So any point which is lying outside, that is this entangled state, what will happen is that I will be able to distinguish between this set and this particular point with the help of a hyperplane. That means, what is the meaning of this one? This basically answers this question. In fact, in our school days, we have done this kind of a problem, that I am given a line, and then I am given a point, and then I am asked that on which side of this line the point lies. We actually gave answers to this question. So this concept of this witness is actually generalizing this idea. So if suppose this state over here lied over here, then what will happen is, since both of them are lying on the same side of this, I will not be able to tell anything. But if it lies over here, then with the help of this one, I can tell that this is entangled. Suppose a state lies over here. Then suppose I take this is my indicator function. This indicator will not do anything, will not be able to tell me anything, because they are lying on the same side, separable as well as this point entangled. But suppose I create this thing, then this line will tell me, okay, this is lying on the other side, so it is entangled. So basically this Hahn-Banach theorem is talking about that separation. It is telling that if your set has those two desired properties of being convex and closed, you can separate the points lying outside it with the help of a hyperplane. That is what it says. It is not telling you how to construct that hyperplane, but it is telling that, okay, such an hyperplane will exist. And that is known as an entanglement witness. That means why it is that entanglement witness? Because it is actually witnessing entanglement. That is, the shared state that you have is entangled or not. That is what it tests. Okay? So this is one example of an entanglement witness. And as you can see that this is an entangled state. If you use this operator, then it will give a negative value. And negative value means that this state is entangled. So we can use this kind of matrices, we can use this kind of operators to test whether a particular state is entangled or not. Okay, now we come, as we now have notions of entanglement, notions of quantum states, notions of the pure states and mixed states, and the notion of measurement. Now let us see this very, very important point of what is known as a quantum teleportation. Question is, suppose Alice and Bob, again my two fictional characters, Alice is here, Bob is here. Whether, now suppose Alice has some unknown qubit. Okay, so suppose Alice has this unknown qubit. that is this. Why it is known as an unknown qubit? It is known as an unknown qubit because Alice doesn't know what is this A and what is this B. Because suppose if Alice would have known what is this A and what is this B, then what will Alice do? He'll just make a phone call to Bob and he'll say that okay, this is A and B. So Bob will be able to generate that state. But Alice doesn't know that. And it is also not possible for Alice to say what is A and B, because if he has to say that, then this A and B can actually have infinite number of possibilities. So if he goes on to do measurement, she will need an infinite number of measurements to find what is an estimation of A and what is an estimation of B. So she has to do an infinite number of measurements. So then again, it is not possible in that way also. So then what is possible? That means the objective is that Alice wants to send this qubit from her end to Bob's end. So that she wants to do. So is it possible? Is it possible that you can send a qubit like this? So this is a qubit. Yes, it is possible. And it was actually shown in 1993 by Professor Charles Bennett and his collaborators that this can indeed be done if you have two things. One, that is you have a quantum entangled state shared between Alice and Bob, and you are allowed to use two classical bits. So if you have these two resources with you, that means you can send two classical bits from Alice to Bob, and you have an entangled source. Then this is possible. Then this protocol can be actually done. So the thing is that, see, if you talk about classical bits, then it is a kind of easy resource because you can just make a call. You can just make a call and then Alice can say, okay, 00 or 01 or 10 or 11, two classical bits. So you can say that. The important thing is this entanglement, because that is not easily available in the market. Today you cannot go to a market and say, okay, give me entanglement, and the person will give you entanglement. Okay, so resource, that is entanglement. Now the thing is that I understand that is a resource, somebody gives me, but somebody might have cheated me. That okay, he is saying that okay, see, I am giving you an entangled state, but it is not entangled. So then I need first to certify that that is entangled. So I can use those criteria that I just showed in the previous slides, that I can show those, use those criteria, and I can use them to say that whether indeed these states are entangled or not. I can use that. Then okay, I am happy, I have got like an entangled state, and then I have to communicate. Okay, so these are the two resources. So this actually was shown by Professor Charles Bennett. So what was this protocol? Let us go to, this is the two resources that I require. I need one entangled state and I need two classical bits. So these are the resources, two resources that are required. So then how is this done? Okay, so as I said that whenever so as I said that whenever this kind of a situation happens, like I need an entangled pair shared between Alice and Bob, then what happens is that there should be a source. So the particles that now Alice and Bob are sharing with them might have interacted long ago, and one particle after that has been given to Alice and the other state has been given to Bob, and as I said that they are sharing this entangled state. So this is the shared pair. So Alice and Bob, and this is the pair that they are sharing, and this is the data qubit. So what is this data qubit? This data qubit is this qubit, unknown qubit, that Alice wants to send to Bob. That is, you can say that it is represented by this alpha 0 plus beta 1, or you can take it A0 plus beta 1, the single qubit thing. Okay, there seems to be another question. Let me see. Yes, this is a very good question. As Mr. Vijay has pointed out, that you have something like this quantum internet. Yes, indeed, you have something like this quantum internet, and people are actually it's in a very nascent stage. What they do is that that in that particular case, this game that I was talking about in the very beginning, that this non-local game that Bell actually first conceptualized, that you can have share some correlations between Alice and Bob, which can help you to do some kind of a communication thing. So what happens in a quantum internet or a quantum network is, so you can imagine that at each and every position, suppose just for the sake of understanding, there are 10 nodes. So Alice, Bob, Charlie, David, all of them are sitting, 10 nodes. So basically what they have is that they can have a 10 particle system shared between them, and that is entangled. That is having some feature which is known as non-locality. They are entangled, and what happens is that they are using these correlations to communicate between themselves. And what you now have is you have some kind of a network between them. And sometimes this is also right now people are working on it, that is network non-locality. Okay, and then they are using this for coming up with this idea of a network where you can in the near, not in the near future, I should say, like some time from now, you have a situation where people are actually able to use this quantum nodes, this quantum non-locality over there, and they can share that. Okay, they can use this to develop a quantum internet. So this is one very important thing that people are right now working on. But see over here, this thing is there, that please don't get into believing this, that this is something that I should like to emphasize, that you have quantum information, you have quantum computation, people are trying to come up with some very good ideas, but that does not mean that it has surpassed all kind of classical computational tasks. The situation is not that. The situation is that the main idea behind is that, can you come up with some trick where first of all you have to choose a task. After choosing that task, you have to show that your best known classical procedures, you can get a result. But using a quantum resource, using a quantum trick strategy, you can surpass that. Then it will show that you certainly have some advantage. So basically right now when you talk about quantum computation, this is one of the most important things that people need to realize. Please don't get into this feeling of, okay, it's a very happening thing, okay, good, people are working on it. But that does not mean that it is breaking everything. It is surpassing everything. It is not like that. This is one of the reasons. Second reason is that if you indeed have to have some kind of an advantage, then you have to work with lots of qubits. And when I mean lots means lots, billions and millions of qubits. So you can now very well imagine, as I already told, that quantum systems are very delicate to handle. They will get corrupted. They will, even if with the slightest of environmental interaction, they will not be able to give you the desired results. You may get a very poor result. So this, when you have millions of qubits, to have a precise control over them is very important. That so far we have limitations. We don't have that power. We don't have that technological acumen right now. And this actually has been pointed out by several leading researchers like Professor John Preskill from Caltech and many other person who has told that please don't get carried away by this thing. It is important to see what are the deeper aspects and to see how can we actually achieve such kind of a control. So that is very, very important to realize. You do have some quantum algorithms, you do have some computational tasks that indeed quantum information, quantum theory has like given some very promising features. You do have that, like the Shor's algorithm, like this teleportation that I've been talking about. You do have that, and in fact quantum teleportation has been experimentally realized. It is not that it is only theoretical proposal, it has been experimentally realized. Okay, so you have this dense coding protocols which has been experimentally realized. But again, you have to take everything with a pinch of salt. You cannot just say that, okay, this is happening, everything has broken up. Because today if you go to a market and if you ask, okay, give me a laptop a quantum laptop, nobody will be able to give you, because that is the thing that we want to be very sure of. We need to be very sure of that, whether we have gained that precise control of so many qubits taken together. That is the thing that we should be very careful about before we can come to any sort of any conclusion. Okay, so there are indeed certain features, there are indeed some tasks where quantum advantage has been shown, like teleportation, but again there are some tasks for which quantum computation and in fact quantum processing protocols are also very poor, not very promising over there. So it's not like in that particular area. The subject is developing, and the other thing is that you must have come like across a particular term that is this noisy intermediate scale computing that goes by the name of NISQ, NISQ. So over there also, it is just a very, that is a very like fantastic thing that people have now come to this particular thing that, okay, quantum computers can be realized, but that is in the noisy intermediate scale, NISQ scale. So for that, I will like to suggest that there is this very excellent article by Professor John Preskill from Caltech, who has told what are the promises that this NISQ devices have. So I suggest, I can request all of you to just go through that particular article. Okay, so we have to take, as I said, everything with a pinch of salt. Thank you for bringing up this question of this quantum internet. Thank you. Okay, so what I was doing over here, I said that this is the data qubit that Alice wants to send to Bob. So what will you do? She will do a Bell state measurement. That means she will do, so this is, she possesses this one, she possesses this one, so she has two particles in her position. So she will do a Bell state measurement. Bell state measurement, that means a measurement done in that Bell basis. I was talking about that Bell basis earlier. So whenever you do a measurement, it has to be done in kind of a basis. So what is that basis? I'm telling you, you have this black box. Black box means that your quantum state comes inside, and you can think that there is a knob in that. So whenever you have that 0, 1, these are the two nodes. If you have two qubit systems, 0, 0, 0, 1, 1, 0, 1, 1, if you are doing it in that basis, similarly Bell basis, B1, B2, B3, B4. So what you do is that you do, whenever you do a measurement, you do in some kind of a basis. That means you imagine, you visualize this, that the quantum state goes in, you have this apparatus, it has a knob, and that knob, I set it to B1, it will give me some result. I set it to B2, it will give me some result. So it is done in the Bell basis. So when you do that measurement in the Bell basis, what happens is that Alice gets 4 possible outcomes. Okay, the possible outcomes are 0, 0, 0, 1, 1, 0, and 1, 1. So see, these are all classical bits that she is getting. What she will now do is, as I said, that she has to have this resource where she can communicate to classical bits. So what will Alice do? Alice will pick up the phone. Hello Bob, result is 0, 0. So 0, 0 goes to him. Now what will happen? What will Bob do? After he gets to know about this particular result, then as I said that they were sharing an entangled pair. So what will Bob do is, on his particle, he will do a unitary operation. Unitary operation means that when you are transforming a quantum state. So depending upon what classical bits Alice has transmitted to him through that phone call, Bob will choose a suitable unitary operator, and he will operate with that on his particular state. That will give this thing, that is alpha 0 plus beta 1. But as I said, that this is the most ideal scenario. But in this most ideal scenario, Alice and Bob is sharing a maximally entangled state. Maximally entangled state between Alice and Bob. Now why, if they share this maximally entangled state, what will happen is that she wants to send shy, and Bob also gets shy. That means he gets the exact state by using this unitary operation on his end. But If it is not maximally entangled, if it is some entangle which is not as like powerful as the maximally entangled state, if they use some other entangled state, then what will happen? This psi over here will come as psi dashed, which is a bit different from psi and psi dashed. So then one needs to calculate the fidelity between them. What is this fidelity? This fidelity actually measures the proximity between two states. That means how much is psi dashed equivalent to psi, how much it is related to psi. So that is measured by fidelity. So what happens is that if you use a maximally entangled state as the pair shared between Alice and Bob, that fidelity will be 1. That means you will get the exact state. But if it is a lesser entangled state, then that fidelity won't be 1. But the advantage is that if you use, instead of an entanglement, you use classical correlations over here, then the fidelity will never cross 2 by 3. Again, another game. The game is that if you use any kind of classical correlation between Alice and Bob, they will never be able to break this fidelity 2 by 3. You can never surpass it. This surpass, that means you can breach, you can go beyond this value only when you are using an entangled state. So that means if you use classical correlations between Alice and Bob to exploit this, you will never get a fidelity more than 2 by 3. But if you allow an entangled state, a proper entangled state to share between Alice and Bob, they can use it as a channel, and that channel, particular channel, will give them a fidelity of more than 2 by 3. If you give them maximally entangled state, they will be very happy to get that. But then again, it will come with some cost because it is a maximally entangled state. So the thing is that this teleportation scheme or this protocol of teleportation uses what? Uses an entangled pair shared between Alice and Bob. And this, then Alice can do a Bell measurement on her 2 particles, then share the output with Bob, telephone call, and then Bob can do some unitary operation on his particle and he will get this. Now this thing that Bob does some unitary operation and gives this state, it happens because they are sharing that entanglement between them. Otherwise, this would not have been possible. Yes, this projection operator that you came to know in quantum computing and quantum information is an operator which will actually, when you have a vector space, then you have a vector space and you have some subspaces. Subspaces are subsets of this vector space, and they are itself forming a vector space on their own. So a projection operator means that when you operate it on a vector, then it will be getting projected on a particular subspace. So that is the projection operator. A very simple example is like like if I say that this is your 2-dimensional plane and like this is your line, then you can have a projection of this line on the x-axis. So that can be done by an operator which will act on this vector and it will give a projection on the x-axis. So the projection operators over there in more general cases acts in the same way. That is, you have a certain vector in higher dimensions and then you are projecting the vector into a particular subspace, which is again a vector space on its own. So that can be done, because in quantum theory what happens is that everything is the whole story of quantum theory is actually about measuring observables. The observables are basically self-adjoint operators whose value you want to measure. That also you have learned in your one of the sessions on the postulates of quantum theory. Okay, so see, I want to now end over here. That over here today, what we talked about that what is this that we are looking for in quantum information and computation? That is, we are looking for some kind of a correlation which cannot be provided by the best known classical correlations. And one of the such correlations that we studied today was entanglement. And we saw that how can we define entanglement. We then saw that how can entangle be detected, because the definition by itself doesn't give you any constructive way to detect entanglement. And then we saw that particular entanglement, when you have, can have very, very counterintuitive features. And then what we have seen is like how can that entanglement be used for a very significant protocol that is known as the teleportation protocol. And as you can see that in this like the teleportation protocol, that I want to say that in this teleportation protocol, this was only about the 2-qubit systems. That means Alice and Bob is sharing a 2-qubit entanglement between them, but it can be easily generalized to high dimensions, like 2q-3 entanglement, or entanglement where the dimensions are 4. In fact, it can be expanded to when it is not about only Alice, Bob, but there is another person called Charlie. So you can actually modify and generalize this to any high dimensions, and those work has already been done. So this is the important thing, to identify correlations, to detect such correlations, use them in an information processing protocol or a computational task. So that is what I wanted to convey with you. So I think at this moment I would like to thank all of you for your patient hearing. Thank you. Thank you very much.
Sir, on behalf of Photonics Valley Corporation, we would like to thank you. Your speech was really informative. And apart from it, even a student like me, in fact, when I say student, actually, I'm not an IT professional. I'm a functional professional, but even though I'm a functional professional, I could understand most of the concepts which you have been explaining. So I'm sure the engineers there sitting out there and listening to this will surely be enriched with knowledge, with the inputs that you have given. So on behalf of Government of Telangana, on behalf of Photonics Valley Corporation, we would like to thank you. Thanks a lot, sir, for joining us.
Thank you. Thank you. It was a very humbling experience for me too.
Thank you very much.
Thanks a lot, sir. Now, ESAT team, you can close the session. ESAT team, you can close the session.
Yeah,
You
close.
can close.
Thank you very much, sir.